Today we're diving into dynamic scaling of unit tests for code reward modeling.
Okay.
It's a research paper that explores how to make large language models, or LLMs, write better code. You know those AI chatbots that are making all the headlines?
Yeah.
Well, they can write code, but they don't always get it perfect.
Right.
This research explores using LLMs to write unit tests, which are like mini exams for code,
Yeah.
to improve the accuracy of other LLMs writing code.
Interesting.
So the researchers actually found that the more unit tests they used, the better the code became.
They did.
Interestingly, this held true even for smaller LLMs, which achieved comparable results to larger models just by increasing the number of tests.
It's like you're learning to code. The
Okay.
more practice problems you tackle,
Uh-huh.
the better you understand the concepts and avoid common mistakes.
Right.
And it's similar for LLMs.
Okay.
By subjecting the generated code to a larger battery of tests. The researchers forced the model to address more scenarios and potential pitfalls,
Yeah.
resulting in a more refined and robust solution.
So it's about pushing the LLM to consider a wider range of possibilities and edge cases.
Yes.
The paper mentions a specific technique,
Yeah.
dynamic unit test scaling.
Okay.
What's that all about?
So it's about figuring out how many unit tests are needed for a given coding problem.
Okay.
Instead of applying a fixed number of tests to every problem,
Right.
they adjust the amount based on the estimated difficulty of the task.
So they're trying to be efficient with their resources.
Yeah.
Wouldn't running an excessive number of tests for every simple problem
Right.
be a waste of computing power?
Yeah.
How do they even estimate the difficulty of a coding problem?
They use a technique called language model probing.
Okay.
It's like giving the LLM a little quiz about the coding problem
Wow.
to assess its understanding.
Got it.
Based on the LLM's performance on the quiz, they can gauge how tricky the problem is and allocate a proportionate number of unit tests.
Yeah. So it's similar to studying more for tougher exams.
Right.
You put in more effort when the challenge is greater.
You do.
This dynamic unit test scaling approach seems pretty effective.
It's significantly improved performance across different LLM sizes and types. Even large, powerful models like the 70B parameter version of Llama saw gains.
That's impressive.
Yeah,
And they developed their own lightweight unit test generator, right?
they did.
Tell me more about Coder M8B.
So Coder M8B, it's remarkably efficient at generating these unit tests. What's particularly interesting is that Coder M8B produced diverse unit tests, offering various perspectives on the code,
Okay.
which led to higher overall code quality.
Yeah. So this means that the model isn't just churning out repetitive tests.
Right.
It's coming up with creative ways to evaluate the code from different angles.
It is.
That's pretty remarkable.
Yeah.
A smaller 8B model generating a diverse range of tests to improve the output of a 70B model.
This leads to an interesting thought.
Okay.
While the research focused on Python, could Coder M8B and the principles behind it
Yeah.
be adapted to other programming languages?
That's a good question.
Imagine AI coding tools that could work seamlessly across various languages.
Yeah.
That would be a game changer for developers working with diverse tech stacks.
It would definitely make AI coding assistants more versatile and accessible to a wider range of developers. Can you tell me a bit about how Coder M8B was created?
The researchers started with existing data sets like code feedback filtered instruction and Taco.
Okay.
These data sets contain code and instructions, making them ideal for training a unit test generator.
Right.
They filter out any entries not suitable for unit testing, like tasks that relied on random elements or external resources.
So they ensure that the data used to train the model was specifically geared toward the kind of problems that unit testing is designed to address.
They did.
What happened next?
They restructure the code into a functional format, making it easier to generate unit tests. Then they used a powerful LLM,
Okay.
Llama 3.17B, to generate a variety of unit tests based on the code and instructions from these data sets.
Okay.
They ran these tests on the actual code solutions to determine whether they passed or failed.
So they created a labeled data set of unit tests
Yeah.
by running them against the code and seeing the outcome. Interesting.
And then they went a step further
Okay.
and used feedback from the Python interpreter to refine the tests that initially fail.
So they weren't relying solely on the 70B LLM.
Right.
They also used real-world execution feedback to improve the quality and accuracy of the tests.
To further enhance quality control,
Okay.
they generated incorrect code solutions using a weaker model.
Hmm.
Any unit tests that incorrectly passed these flawed solutions were filtered out.
So this ensured that only the most rigorous tests capable of catching errors were included. That's clever. It's like a double check to make sure the tests are doing their job properly.
It is.
How did they use this refined data set to train CoderM-8B?
So they took the labeled unit tests, the corresponding code and the instructions, and used a technique called supervised fine-tuning on a smaller LLM, Llama 3.18B.
Interesting.
This process is similar to how we learned from examples. They essentially showed the 8B model examples of good and bad unit tests, teaching it to generate high-quality tests on its own.
And it worked.
They did.
The 8B model was able to learn how to generate effective unit tests.
The paper found that the more data used to train CoderM-8B, the better it performed. This suggests that with sufficient training data, smaller models can achieve impressive results in specialized tasks like unit test generation.
It's fascinating how they've used different LLMs, each with its own strengths, in different stages of the process. A larger one for initial generation and a smaller one for refining and specializing the output.
Right.
The paper mentions that they also explored the impact of filtering out lower quality unit tests during training. What do they find?
Filtering out lower quality unit tests during the training process led to a substantial improvement in the model's performance. It's like focusing your study efforts on the most important material instead of getting bogged down in irrelevant details. By removing the noise of ineffective tests, the model can learn more effectively from the remaining high-quality examples.
This is an intriguing study that highlights the potential of unit test scaling to improve LLM-based code generation. But it also brings up an interesting question. Could these techniques be used to teach LLMs entirely new coding concepts?
The paper doesn't delve into that aspect. The research focuses primarily on utilizing unit tests for evaluating and selecting the best code solutions from a set of generated options. However, your question opens a fascinating door to a realm of possibilities.
Could we potentially train LLMs to become even more adept at coding by using increasingly complex unit tests as a form of instruction? Instead of just using tests to check if the code works, we could use them to guide the LLM's learning process. What other areas for future research do you think this work opens up?
One area could be exploring the incorporation of different types of feedback in the unit test generation process. Currently, they are using pass-fail results from code execution, incorporating feedback from human code reviewers, or analyzing the code's performance characteristics could provide valuable insights.
That would add another layer of sophistication to the training process, leading to more nuanced and comprehensive unit tests.
It would.
It would be like having a seasoned developer provide feedback on the LLM's work, helping it to understand not just whether the code functions, but also if it adheres to best practices and is well structured.
Another interesting area is how these techniques could improve code repair. Imagine an AI that identifies bugs through unit testing and suggests fixes.
That would significantly boost developer productivity.
It would.
Freeing them from the often tedious task of debugging. It would be like having an AI pair programmer that not only catches errors, but also helps you fix them.
Exactly.
Of course, this research focused on relatively self-contained coding problems.
It did.
How do we adapt these techniques to real-world complex code bases?
Adapting these techniques for large, complex code bases presents a significant challenge for future research. The intricacies of dependencies, integrations, and the sheer scale of real-world projects require a different approach than what's been explored in this paper.
This research shows how combining LLMs and automated unit testing can make writing and debugging code faster and more reliable. It's exciting to consider the potential impact on software development.
This deep dive into AI-powered code generation and testing has been insightful.
It has.
This research certainly pushes the boundaries of what is achievable with technology.
Well, thank you for joining us on this deep dive.
Of course.
Until next time, keep exploring, keep learning, and keep asking those thought-provoking questions.